Hi, welcome to Chapter 6, Part 4, our last part of this chapter, where we're going to talk about electron configuration and how it relates to the periodic table. So, how do we arrange our electrons in our sublevels and energy levels that we talked about in our last video? So, electron configuration is a way of arranging the electrons within the various orbitals around the nuclei of the atom. And there are three rules that we have to follow when doing this. The first one is Aufbau's principle. The second one is Pauli exclusion principle. And the third one is Hund's rule. So let's talk about Aufbau's principle first. First of all, Aufbau is not a person. I thought he was for many, many years. But it actually is a German word that means to fill from the bottom up. So we're filling from the lowest energy to higher energy. And here, if you can see over here, it says increasing energy. So here is low energy. And here is high energy. The further away from the nucleus you get, the higher the energy. So the first sublevel we're always going to fill is the 1s. After the 1s, we'll fill the 2s. After the 2s comes the 2p. Then the 3s, then the 3p, but then when we get to the 4s and the 3d, it gets a little confusing because what happens is the 4s is actually lower energy than the 3d. So you fill the 4s before the 3d. Even though it is a higher energy level, the actual energy of that sublevel is lower than the 3d. Remember, the more electron repulsions you have, the higher the energy. So there's a lot of electron repulsions going on in this 3D, which makes it slightly higher than the 4s. The second rule or principle is Pauli's exclusion principle. And what he said is that no two electrons can have the same four quantum numbers. So if you remember your quantum numbers, there was your principal quantum number, then there was the L, then ML, and MS. So you can't have the same four numbers to describe more than one electron. So because of that, no two electrons can have the exact same energy. And that means that every electron has to differ by at least one of the four quantum numbers. As a result of this, in an atomic orbital, it may contain at most two electrons, and the electrons, so this is your orbital, the electrons in that orbital have to be spinning in opposite directions. And we show that with an up half arrow and a down half arrow. And the third is Hund's rule. And Hund's rule says that when you are filling a sublevel, you want to maximize the same spin. If you maximize the same spin, that will give you your lowest energy. Because if they are spinning in the same direction, there are less electron repulsions. Okay? So what does that really mean? If you look at this diagram here, look at carbon. We are filling the 2p with two electrons. Instead of putting two electrons in the first box, one up and one down, you have to put one up in each of these boxes, and this maximizes the amount of the same spin. Your third electron down here for nitrogen would go in here. You don't actually start doubling up these boxes until you have one in each. So if you had to do 2p4 instead of 2p3, you would put a down arrow here and then work your way across. So before a sublevel can have two electrons in an orbital, you have to make sure each orbital in that sublevel has one electron. So let's just take the p. It has three orbitals. You can't have two electrons in an orbital unless there's one in each of these first. That is Hund's rule. Why is he doing this? You want to maximize same spin. So all of this leads to the electron configuration notation, where here hydrogen has 1 electron, and we always fill our lowest first, which is 1s, and there's 1 electron in there. So this 1 in the front is your N, your energy level. S is your sublevel, and the number up here is the number of electrons. So here is the electron configuration for oxygen. If you add all of these superscripts, that should tell you how many electrons are in oxygen. And it will, if your element is neutral, remember your number of electrons equal your number of protons. So it can help you identify what the element is. So here is a continuation. So electron configuration is the way the electrons are distributed in your atom. And when we are writing it for the ground state, our lowest energy state. Unless it tells us our atom is excited. Okay? So here is an example of the last sublevel that was filled. The number in front is N, your principal quantum number, or your energy level. The P tells you your sublevel. Remember, which is L. And the 5 tells you your number of electrons. So if I wanted to do my 4 quantum numbers for 4p5, N would be 4. L, remember L, 1, 2, 3, S, P, D, F. So we have P, so L is 1. So here is our 4p, which has 3 orbitals, and we like to label them -1, 0, and 1, and we're putting 5 electrons in there. Remember Hund's rule, you have to have 1 up in each before you can double it. The last electron I filled was this one here, which happens to be on the 0 line, so that's my ml. And my spin in this case is pointing down, so it's -0.5. So here are my quantum numbers. I erased them by mistake. So those were the quantum numbers. Orbital notation is the arrows, when you're drawing the arrows. Okay, and this is very useful to see or help you calculate your ML, because you see, in this case, the last arrow you drew was here. So what are my 4 quantum numbers for this? My last electron I drew was in the 2p, so N is 2. L is P, remember. S, P, D, F, so L is 1. ML in this case is on the 0. And my spin is -0.5 because it's pointing down. Okay. Now, writing electron configuration, as we get to some of our larger atoms, it gets to be very, very long. So there is a shortcut method, or the noble gas notation, which helps reduce the amount of things that you're writing. So if we take sodium, this example right here, sodium. Sodium has 11 electrons, so it's 1s2, 2s2, 2p6, 3s1. Add these up, that's 11, right? So what you do is you look at the periodic table and you find the noble gas that comes before sodium. The noble gas that comes before sodium is neon, and neon has 10 electrons. That takes care of this. So then all you write is what comes after that. And this is called your noble gas notation. And in a few slides, I'm going to show you a periodic table which helps you do this even quicker and easier. So again, the transition metals are unique because they are actually, we'll be filling the D block in the transition metals. And before we could fill the 3D, we have to fill the 4s. Remember, the 4s is lower energy than the 3D. So the transition metals are in the D block, so we're always filling the 4s. We're always filling the higher S before we fill the D. And because these energies are so close to each other, that's why the transition metals can have more than one oxidation number. Because you could lose electrons from the 4s or the 3D. Or if you're in it, that's actually just for the first row of the transition metals. The rare earths are those two rows at the bottom of the periodic table, and they are your F block. So that's when you start filling your F sublevels. Okay? So if you look here, here is the periodic table. What they did was they took the two rows that are normally below and they stuck them in the periodic table where they belong. Normally you don't see the periodic table looking like this because it makes it too long to fit like on a regular piece of paper. But what I want to point out is that here are your row numbers, or you could think of these as your ends. And when you look at the periodic table, when you're filling your S and P, the S and P that you're filling is equal to N. What do I mean by that? So take, for example, I am writing the electron configuration of this element. N is 2, and it's in the S block. This is my S block. So it's going to end in 2s. How far is in it? 1, 2. So it's going to end in 2s2. So that goes with the p's also. Notice this p is in the second row, and it's 2p, 3p, 4p, 5p, 6p, 7p. Notice there is no 1p. 1p does not exist. Now your D block fills the n minus 1. So here, if you look, is n is 4, and we are filling the 3D. So say I wanted to write the last sublevel for this element. It's in the 3D. How far in is it? 1, 2, 3. So that ends in 3D3. Your F block is n minus 2. Because notice this is a 4 and this is a 6. Now to put it in a format that you're going to see more common, here is the way you normally see the periodic table. And just know that these guys are fitting in right here and right here. Don't forget to count them, okay? So say you wanted to write the electron configuration for this element here. You just go across. Oh, I'm filling the 1s, and there's 1, 2 of them. I'm filling the 2s, and there's 1, 2 of them. Filling the 2p, and there's 6 of them. Then I'm filling the 3s, and there's 2 of them. Then the 3p, 6, 4s, 2, 3d, 10, 4p, 1, 2. You see how you could just use this periodic table to write the electron configuration? So it's very handy. As long as you remember how they are related to the row numbers. Now we've assumed everything follows this rule, and that is not case. There are some anomalies. And your anomalies occur mostly in your D and F block. Because those sublevels, their energies are so close to each other, the electrons tend to jump from one to another. An example here is for chromium. Chromium, if we follow the pattern, should look like this, but in reality, this is what you get. So what happens is one of the S's jumps into the D. And why is this more stable or lower energy? Because what you end up having is two half-filled sublevels. So here, which is more, which is lower energy than having a filled S level and then a randomly filled amount of D. So here, I circle the elements that do not follow the electron configuration. And if you have time, go ahead and look at them and see how they differ from what they should be and see if you can explain why this is occurring. And this is related to their charges, their oxidation numbers. All right, so let's try to write the electron configuration for a couple elements. So the first one is oxygen. So here is oxygen right here on our periodic table. It is in the P block. It is in the second row, and it is 1, 2, 3, 4 in. So 1, 2, 3. So this is where oxygen is, right here. So we start with our 1s, and there's 2 of them. Our 2s, 1, 2. And we go to our 2p. How far into the 2p are we? 1, 2, 3, 4. So that is our electron configuration for oxygen. Now let's do it for tin. But it says let's do the shortcut method, which is the noble gas notation. So what is the noble gas that comes before tin? I don't know if you can see it, but it is krypton. So we're going to put krypton in brackets, and that's in 1, 2, 3, 4. So 1, 2, 3, 4. So here's krypton. So what comes after krypton? We're starting here. We have 5s2, 4d10, and we are ending in the P block 2n, so it's 5p2. So that is the shortcut way to write tin. So all of the electron configuration we've been writing so far are for the ground state. Remember, your ground state is lowest energy. But we know that atoms get excited. That's how photons are produced. So how would it look if we had an excited state? How do we draw the electron configuration for that? So here is potassium's ground state electron configuration. If you are exciting it, it means that you are moving an electron from a lower energy level to a higher one. So here is one possibility. Notice here, this is 3p5. It was 3p6 here. So one of these came up and now made this 4s2. This is an excited state. Another option is here. How does this differ from our ground state? Well, notice the last sublevel that we're filling. It jumped from a 4s1 up to a 4p1. So this is excited. How does this happen? Well, let's look at this example for carbon. Here is our ground state, and this is our orbital diagram. I add energy, which causes one of my electrons to jump. In this case, this electron jumps up to here. So this is the excited state. It won't stay there very long. It will fall back down to where it belongs, and then it'll release a photon. What about ions? Now, ions, there's two types. You have your cation, which is positive because you lost or you're losing electrons. And then you have your anion, which is negative because you're gaining electrons. So here is sodium's ground state, and it has a +1. So this means it lost 1 electron. And you always lose your electrons from your outermost energy level, which in this case would be your 3s1 goes away. Okay. Now this one here has a -2, which means it gained 2 electrons. So that is why now this 4 has become a 6. Now what if you're a transition metal? Okay, transition metals, remember we fill our 4s before our 3, we fill our s before our d. It doesn't have to be 4s and 3d, that's just the first row. So here is the normal ground state. When we lose our electrons, because this is losing, 2 electrons will be lost. You have to lose them from the energy level that is the furthest away from the nucleus first. The 4s, because this is a 4, is further away than the 3d. So we will lose these 2 electrons first. And that is why this is the electron configuration for our zinc ion. Okay? After you lose the 2 and the 4s, then you can start losing from the 3d. But you have to, even though we fill it 4s first, then 3d, when we lose 4s and then 3d. Okay? And that's it for part 4.